So there's two more really quick ideas that I want to talk about. One is this notion that if we can compute the Nusselt number, we can compute the friction factor, or sorry, the coefficient of friction, then we can actually relate the two of them, right? There's this relationship, at least according to the Prandtl number, between the boundary layer growth for both momentum and thermal. And so if that's true, then there should be a relationship between the friction coefficient and the heat transfer coefficient. And like, why would we care about this? I guess we care about it because it's really hard to measure the heat transfer coefficient. It's a lot easier to physically measure the friction coefficient, right? You just look at the difference in pressure across two positions in the flow. If you can measure the difference in pressure, you can actually measure or approximate the heat transfer coefficients that are involved. So this idea is called the Reynolds analogy. And let's kind of see how we arrive at it. So we're going to say Nusselt x approximately equal to x over delta t, where then delta t is approximately x over Nusselt, just rearranging. Coefficient of friction says approximately 2 mu over rho u infinity delta m, rearranging delta m approximately 2 mu over rho u infinity cf. So let's take these two and let's combine them. But let's do that by saying delta t is equal to delta m. So this is, again, like a Prandtl of approximately 1. This is not always going to have to be the case, but let's just start this way so we can equate these two expressions. Then we get x over Nusselt is approximately 2 mu over rho u infinity cf. And then we can write it in terms of Nusselt number. So Nusselt x is approximately rho u infinity x over mu times cf. This bit here is, again, our Reynolds number. So what we're saying here is actually Nusselt at a position x is approximately the coefficient of friction times the Reynolds number over 2. So this is a way that we could just relate, like I said, something related to the friction, the pressure drop, to something related to the heat transfer. There's a more exact model than this approximate one, and it's called Chilton-Colburn. And it says the Nusselt number is approximately equal to Prandtl to the 1/3 times the coefficient of friction times the Reynolds divided by 2. So this would be the one that you'd probably want to use because it also incorporates the Prandtl number into the equation, meaning that we don't have to make the assumption that delta t and delta m are the same. So the last thing I want to mention is this idea that we've talked about local heat transfer and average heat transfer. Obviously, there's a relationship between those two. And the way that you go from the local, which is what we're predicting with this boundary layer model, and the average is just an integral, an area average integral. So let's look at maybe the profile. So if we plotted as a function of coordinate x, our heat transfer coefficient hx, where this over here is x equals 0. What you'd have again is this initial infinite heat transfer coefficient, and it sort of quickly drops down and then tapers out. And so what we're saying is if I want to, let's say I want to compute the average heat transfer coefficient up to this position L right here. So I want to know over the entire span what is the heat transfer coefficient. What I'm going to do is I'm going to take the integral of this entire area here inside and then average it by the distance that I'm integrating. So just in general, we'd say h bar is equal to 1 over x integral from 0 to x of hx dx. That's going to give us the average heat transfer coefficient. In this case, as I've written it, it would actually be, as we apply it, h bar is equal to 1 over L, 0 to L, hx dx, where your model for hx is going to be, let's say, related to the boundary layer thickness model, or perhaps we're using a correlation for that. So this is the way that we get to this case. If you wanted to estimate, let's say, heat transfer coefficient for just part of the array, right? Say this is x1, and now instead of this being L, this is x2. We would just write it the same way, but it would be like h bar is equal to 1 over x2 minus x1, integral from x1 to x2 of hx dx. So those are going to be kind of some different approaches to computing the average heat transfer coefficient. When it comes to evaluating things like conductivity, right? So conductivity is often actually a function of temperature. Conductivity is usually going to increase with temperature. So there's this question of, like, should I be evaluating conductivity on the surface at the surface temperature here? Should I be evaluating it at the edge of the boundary layer? The answer to that is that we would actually be doing what's called a film temperature. So we're going to evaluate properties at T film. And this is basically the average temperature of the film. So that's going to be Ts plus T infinity over 2. If Ts happens to be a function of x, in which case T film is a function of x, we could just take the highest possible Ts, the lowest possible T infinity, and average there. Or maybe you could compute T film as a function of x. It just kind of depends. But those are just different ways that you can approach computing it. So this is the overall introduction to boundary layers and convection, and we've gotten to the point where we can express things non-dimensionally. Next time we're going to be talking about how you apply these things in correlations.